this is the title is there, the contributors are there. Well, I'm proud and happy to be part of the eMagic consortium, which is led by the CDTech, very capable people. Great pleasure to work with this leadership. And I believe that this consortium is really I would say that this consortium, if there is a chance for practical, relevant magnesium ion batteries, this consortium is the playground. This consortium provide, I think, the most important frontier and possibilities to examine the feasibility of magnesium battery technology. So I'm very happy to be part of it. Now, the slides will be very busy for people who can read fast. So there is a lot of information there. I'll explain everything, but I loaded the slides with information. Also, of course, the presentation can be distributed and shared with you. So let's start with an anecdote. In nature, magnesium is used for photosynthesis. So in nature, use magnesium for harvesting. We are struggling to use magnesium for storage. And if we talk about storage, of course, it relates to green storage because of the abundance of magnesium metal. So we have an interesting relationship here with magnesium for storage for harvesting by nature and storage by us. This is the agenda of my talk. We'll talk about basic problem of DME MgTFSI solutions and in fact, all conventional infrared solutions. We'll talk about necessary conditioning process, and then we'll talk a little bit about impedance spectra and the difference between the magnesium TFSI and magnesium borate electrolytes. We describe a plethora of solvent effects, which are interesting, important, because they may determine potential and rate capability, and also an interesting role of adsorbed chloride species. And this is also important to say something about the role of possible chloride presence in magnesium battery solutions. So what I show you here are voltammograms of magnesium deposition dissolution processes, and in the left, in the upper left, you can see the situation with the magnesium TFSI DME without chloride, and it's very lousy. When we add magnesium chloride, we have interactions. The chloride, what is the problem here? I'll show later, but there are very strong complexes of magnesium with DME that make all reaction of magnesium cations very lousy. Both intercalation and deposition. So when we have chloride, we change the structure of the solution complex, and we enable now more labile magnesium cations from solution to interfaces. But it's not enough. Even when we have chlorides and when we have conventional electrolyte solutions, they're always contaminated with the atmospheric species, and therefore we need some conditioning. Conditioning means that we have to apply some reducing reactions into the solution in order to remove all the atmospheric contaminants that passivate the electrode and lead to high overpotential and low cycling efficiency. We can do it by electrochemical conditioning, simply cycling the solution between magnesium anodes, or using reducing agent like this dibutyl magnesium. So we can do chemical conditioning, reaching the solutions with which we can work. But if we don't use, whenever you use a solution which are not organo-metallic, we don't have any species that can really clean the solution and make it really feasible for magnesium anode. Magnesium anode should be fully barred, unpassivated in order to work. So what we are now studying solutions containing the magnesium borate whoever it is, the formula here. And it appears that here, this electrolyte is associated. So here with this electrolyte, the complex of DME and the complex of DME and magnesium are weaker, and thereby we can have reaction. You can see it here, but we need conditioning. Without conditioning, without removing atmospheric contaminants, we have a lousy reaction. So we need conditioning process that will bring us to a reasonable cycling. But yet there is a question about the cycling efficiency, which is relevant to batteries. So if the presence of atmospheric contaminants in solutions, even in the borate type solution, which are maybe the most promising, the magnesium deposition is lousy, and we see by surface analysis, we see definitely the formation of surface species due to contaminants. But after conditioning, when we reach a reasonable cycling efficiency, the morphology now is much better because we have the very uniform current distribution, because we don't have passivation of the magnesium on a magnesium anode, and then also by the surface analysis, here I show analysis by EDS, show indeed a very minor or negligible contaminants on the surface. When we measure impedance spectra of magnesium anodes, we start with huge impedance, amazingly huge impedance. But with such impedance, the kinetic should be very sluggish. But it appears that once we start to work, the impedance contracts, and we now come up with a relatively low impedance. So we have very interesting dynamic processes. And our hypothesis that was proven in a series of experiments, we did very serious studies of impedance spectroscopy of magnesium anodes. It appears that we have a adsorption that changed the game. So it appears that initially we may have a very high impedance, but once we start the process, we move from inactive to active species. The transport of magnesium ions through the to adsorb add layer change the game. Now the adsorb, it appears that in many solutions, chloride, but even in most of solutions, in fact, whenever we have chloride or any anions, the anions that we have in solutions are adsorbed, even without reaction. They are adsorbed to the magnesium anode, and then so initially we have high impedance, which then and when I'm talking about adsorbed species, I can talk about there may be chloride, there may be even the anions which are formed in the so-called all-phenyl complex solution. But it appears that as we apply current, so and we start to move with the magnesium cations, and this is true for deposition and dissolution. So it goes both directions of application of over voltage. We have contraction of the impedance to values that now enable the reasonable reaction. So it appears that we shouldn't be too frightened, I would say, by the huge impedance that we measure at OCV, because this high impedance is due to adsorption, and the adsorption is dynamic and is very quickly affected once we start the transport of magnesium ions, either to the electrode or from the electrode. Now, looking more seriously about the solutions effect, and I compare here between the magnesium TFSI and magnesium borate. So with magnesium TFSI, it appears that initially we have a very strong complex. So if we try we take cathode now, in the rest of the study, I'll use a cathode and show you the solution effect and surface effect of cathode, because this allow to understand the interfacial and solution effects, which are important and determine the properties. So this is a picture of the complex that we obtain with the magnesium TFSI-DME. We have 3 DME molecules attached to magnesium, very strong solvation shell, and it appears that the TFSI and ions are free. So we don't have association between the anion and the cation. We have very good ion separation. When we add chlorides, we change the game. The chlorides now break the structure of this 3 DME magnesium complex, and we form this type of complexes. We have 3 magnesium, 4 chlorides, and 5 DME molecules, which is around. And now with this change of structure, we can now have reversible behavior, because now magnesium cations are labeled. So this is a situation of Chevrel phase cathode without chlorides, when we have the strong DME magnesium complexes, and when we change the game with chlorides, now we can have the reversible behavior of Chevrel phase, which means now we can enable surface transport of magnesium ion. But we see that the chloride, the effect of chloride is more important. It is not just bulk, it's also electrocatalytic, but this we'll see later. Now let's move to this important borate salt. And here we have a different story, because we have association between the anion and the magnesium, and this association of the anion disturbs the solvation shell, and now we have situation where we can have easier transport of magnesium ions from solution to the Chevrel phase, and this is demonstrated here. So here we don't need chlorides. Apparently, we don't need chlorides, thanks to the different structure, intrinsic structure of the electrolyte solution, when we have association between the anion and the cation. So interim conclusion, the electrochemical obtained with the conditional electrolyte solution are promising from all points of view. When we talk about the borate solutions, they are promising, but yet, and my conclusion number 6 is very important. The borate anion with the CF3 groups is reactive with magnesium metal. So that division never reach 100% in any experiment, and this will affect very strongly my final conclusions. Now, I want to screen with you several surface phenomena that we discovered in recent studies. We take vanadium oxide. Vanadium oxide is very promising cathode material because of the high potential and high specific capacity, and the fact that magnesium ions can be intercalated with certain structure into vanadium oxide, and they can do it reversibly. But interestingly, when we add DME, so we just to understand the problem of solution structures, we did work with acetonitrile solutions with perchlorate, and we add DME, a small amount of DME, and we completely change the behavior. So if you take the black, you take the black curve, which demonstrates reversible behavior in acetonitrile perchlorate solutions. Compare when we add the DME to the same solution, we see very sluggish we see very sluggish behavior, less capacity, and also a more lousy electrochemical response. So here we have a demonstration, and by PITT and GITT measurements. These are just results of, I show you schematically work that was carried out, these calculations. The important conclusion from these studies is that we don't affect the solid state behavior. Everything is due to the solution phase and the transport of magnesium cations. So it appears also by looking through a surface analysis, we don't see any unique formation of surface fields. So we don't, the fact that we change, we add the DME and we had lousy electrochemistry is not because of surface changes, chemical surface changes. So from Raman spectroscopy, here you see some, we have some significant changes in this region. We have several regions of Raman spectra, but the changes shown in this region show clearly that when we go from acetonitrile and we add the DME, we form what I mentioned before, very strong complex of magnesium with DME, even if we add small amount of DME, and thereby we change completely the barrier for magnesium ion transport from solution phase to the bulk. So we don't have, it's not interfacial, it's not bulk, it's something which or electrode bulk, it's something which relates to formation of very strong complexes in solution, and desolvation now is the rate determining step, and this is what caused the gap that we see here, the gap in the barrier between electrode without magnesium ions and electrode that underwent a magnesium intercalation. The DME, it appears that DME is a very important solvent, but we have to be aware of the strong bonding interactions between the magnesium cations and the oxygens of DME, and this issue is very, very important, and we have to, in any electrolyte solution, we have to weaken the strong interaction between DME and the magnesium cation. Now, I'm going to the next topic. In the next topic, again, we move. So there's often information here, but and who can read fast can catch it. But I explain. Here we have experiment in which you use Chevrel phase, and we have two electrolyte solutions. One is APC, all-phenyl complex. And here the solvent is THF, and we have a reaction between aluminum Lewis acid and this phenyl magnesium chloride Lewis base, and we form complex species. In THF, we have this complex species. We have a complex containing two magnesium cation, 3 chloride and ion, and 6 THF. This was confirmed by many studies. And in DME, magnesium TFSI, magnesium chloride, we have this complex. This is the cation which is active. Here we have complexes comprising 3 magnesium cations, 4 chloride and ions, and 5 DME molecules. So we have completely different reactive species that are supposed to interact with the Chevrel phase. And now we do electroanalytical studies. Well, I have to, it's a long story. This story can take two lectures. But what I show you here is 2 sets of voltammograms measured in the 2 solutions. And what is important to emphasize that they are not identical, although finally, we have proven, and this is very important, that the solid state reaction is just magnesium, naked magnesium cation diffusion into the Chevrel phase. So the major reaction is the same, but due to surface issues of the different solution active moieties, we have different voltammetric response. So it appears that we have different mechanisms, and each peak now relates to we have when we have Chevrel phase, we have two sets of reactions. We have interactions with two types of sites with the Chevrel phase. So we see peaks that relate to these two types of reaction, and we have some merging between the processes, overlapping. So it appears that in the two solutions, we have different mechanisms. We did studies which are based on, we simply used we studied how the peak, how the CV, the cyclic voltammetric response, is affected by the scan rate. So it's classical electrochemistry. And we, by this classical electrochemistry, we showed that when we take different peaks, like AC, relate to the first and second processes of intercalation in APC and or in what we call ICD, in magnesium chloride, DME, we see completely different mechanisms, and each process now have different mechanisms, while it's clear that the solid state is the same. Why it's important? So we have the conclusion we did that this summarized very thorough studies, and we studied each process. In fact, the process when we have Chevrel phase, it comes with some copper. So the first process, we have to replace copper by magnesium, which is reversible, and then we have intercalation of magnesium inside. So I don't enter into all the details. But why these studies are important? Because we find that they determine the battery voltage and rate capability. It appears that by using different active species, you change the potential and you change the rate capability. And this was clearly shown by the electroanalytical studies that we did. So we had two solutions, which both are important, the APC and what we call ICD, imide chloride, DME. And because we have different species, as I showed, because we have different species, we have different potential and different rate capability. So, and we can talk about a difference of 100 millivolts, and also difference in rate capability, and thereby such mechanistic studies are important. I move to a next phenomena, which is very interesting. Again, we get back now to vanadium oxide, which I believe is one of the most important possible oxide cathode for magnesium batteries. Again, very busy slide, a lot of information, but let's make the whole story simple. So this is the typical, and here we use two solutions. We use lithium TFSI in acetonitrile, so we remove the problem of the ethereal complexes. So now we use for the anode, we use the capacitive anode, and we now concentrate on the cathode. So now we compare between lithium and magnesium. So with lithium, if we compare between lithium TFSI or lithium perchlorate, we don't see difference. Nothing happened. We see reversible behavior. We don't see any anion effect. But when we move to magnesium in acetonitrile, the same system, the only difference is now the cation is magnesium perchloride, magnesium TFSI. We see change. It appears that TFSI is very problematic here. So again, making a long and for all studies that we did, voltammetry, amperometry, we demonstrate how lousy the behavior becomes when we have TFSI anion. Well, TFSI is one of the most important anions that we may have, So this is definitely annoying. So what we found, going to surface studies by XPS, we show that we see a demonstration of the formation of magnesium fluoride on the surface. It appears that in magnesium, we have some interactions of TFSI that enable there is some fluoride involvement from the CF3 group of the TFSI, and we form very thin, nearly very hard to detect, layer of magnesium fluoride, which fully block the nearly majorly block the surface of the cathode, and this is because of the combination of TFSI and magnesium and the surface of the oxide promotes situation in which we have formation of magnesium fluoride on the surface, and this why we have this impedance problem. Now, the last story is very intriguing, and it relates to the role of surface adsorbed chloride complexes. So here we get back to Chevrel phase, and we use now solutions that contain chloride and solutions which do not contain chloride. So here I show you different voltammograms, and I can make a long and complex story relatively short and simple. We take magnesium, a Chevrel phase, and we cycle it in chloride-free, either acetonitrile or in DME, magnesium TFSI, and we have very lousy behavior that you can see here in the upper left chart. Of course, when we move to chloride-containing solutions, then we have the usual reversible behavior of Chevrel phase that everybody knows. But what is very interesting, and we want to understand more the effect of chloride. It's not, we understand that on the bulk, when we have chlorides, it weakens the interactions between the DME and the magnesium. So we have now easier solvation shell for the magnesium ion transport. But when we take, but there is what we discovered here in this study, and this is reflected by the voltammograms. I explained the story, I explained the discovery. We discovered special electrocatalysis by adsorbed species. It appears that when you take the electrode, cycle it few times in chloride containing species, and then you get back to either acetonitrile or the solution which is chloride-free, DME, magnesium TFSI, you receive reversible behavior. We have adsorbed chloride species which are there, and they can promote now magnesium transport from the bulk to the Chevrel cell. So we have very interesting electrocatalytic activity of adsorbed species. By surface analysis, and look at the two the bottom the spectra, which relate to chloride, it appears that even when we take a Chevrel phase and cycle it, that was cycled a few times in chloride containing solution, and now we move it back either to DME without chloride, or even acetonitrile without chloride, and now we take the electrode and measure it. We see chloride on the surface, so we have strong adsorption on the surface, and it appears that and we have adsorption of such species on the surface, and now we have a complex transport from the solution to the Chevrel phase through complexes which are adsorbed on the surface and facilitate the interfacial transport of magnesium from bulk to the Chevrel phase. What is clear that whatever we do, the solid state diffusion is not affected by the solution species. So we have full mechanism, all the scheme, but I can show some. So the chloride anion is part of bigger complexes such this one, which are formed in DME, magnesium TFSI and chloride, adsorbed onto the Chevrel phase surface in what we call ICD. ICD remains imide, chloride, DME. These adsorbed complexes layer reduces the activation energy of the charge transfer reaction state. It's all surface. It's in fact electrocatalysis. During intercalation, magnesium ions and DME molecule leave the complex to form adsorbed CP chloride intermediate species with magnesium. The chloride ion remain adsorbed, and shortly after, through reaction with the solution phase species DME and magnesium base ions, then the intermediate is the Chevrel, is the molybdenum in the Chevrel phase, transformed back to the original adsorbate, which is the species that is responsible for the reversible behavior. So this is being adsorbed, and we have several stages how this species transform, changes structure, and by these reversible changes that I described, we have reversible magnesium introduction through the interface from solution phase and the Chevrel phase. So this is the energetic scheme. Without chloride, we have a problem of barrier, how to move from solution phase and cause the interface, and this is a very problematic reaction for bivalent magnesium cations. But when we have chloride, we have surface complexes that now facilitate through electrocatalysis the reaction, and this is what we see. And now this brings me to the conclusion. Well, I may apologize for the busy slides, but I thought maybe I have I brought a lot of information. People who could read quickly could get more. And when I show this, if I distribute this presentation, now the people will be able to show all the stories, what you cannot really show in a 35 minutes presentation. So very quickly to the conclusion. We are forced to use only etheric solution to keep the magnesium anode unpassivated. This is known from the beginning. All kinds of surface films, formation, and passivation block magnesium anode. We cannot allow any surface film, any irreversible surface film formation on the surface. Any passivation will fully block the magnesium anode. Now, the bivalent nature of the magnesium cations and the strong interactions with the ether's oxygen atoms dictate unique solution and surface interactions that determine the reaction feasibility, potential, and rates. I showed it by different ways. So, finally, the solution structure may be very important, and the nature of the species which work within the solution may affect very strongly the potential and rate capability. So, although the electrode, the solid state host, may work perfectly. In working solutions, the strong magnesium ether complexes are weakened when we have working solution, like when we have chlorides or when we have the borate solutions, and this can be done by either through the presence of chlorides. We add magnesium chloride, and now the chloride changes the structure, and now we have a complex instead of 3 DME, which catch magnesium cations, we have complexes of 2 magnesium. We have 3 magnesium cations, 4 chlorides, and 5 DME molecules. We change completely the structure, but now magnesium cations are loving. What happens in this important electrolyte? In this important electrolyte, this bulky anion with the borate structure is associated with magnesium. This is thanks to the borate, and this substituted isopropyl ligands help to form a bulky cation, which also help to make any complex in solution more disordered. And so here now magnesium is labbing, thanks to the relatively weak structures that can be formed between magnesium and DME when we have association between magnesium and very bulky anion. Now, the presence of chloride is problematic for transition metal oxide cathodes. Surprisingly, TFSI anions are problematic as well. We have passivation, very strange passivation phenomena on vanadium oxide. It may be relevant to other oxides. We detected magnesium fluoride formation. It may be thin, but even one layer can be good enough to block the electrode. When we need interfacial transport of magnesium and we have any ionic magnesium compound on the surface, then it kills our kinetics. I'm concerned that in chloride-free solutions, like even with DME, with this excellent electrolyte, magnesium do not really demonstrate 100% sagging efficiency, probably because this anion is slightly reactive with magnesium metal, and we have evidence for that. So we need some metastability. So we should know that this anion, which is maybe the best so far, is not innocent. We have some interactions, and in order to have magnesium batteries for what we need them for large energy storage, so we need thousands of cycles. And thousands of cycles can be reached when we have organo-metallic electrolytes. So the solution is clean. We don't have any interactions. When we have chloride in solution, we can mitigate the reactivity of magnesium anode, and thereby we may need to use chlorides containing solution even with this excellent anion. Because when we have chloride, we have adsorption on the magnesium. I explained it. I showed the high impedance. This high impedance is very terrible at the beginning, but it's very good because this high impedance that we measure at OCV means that we have add layer of anions on the magnesium surface, and this add layer, if we have chlorides adsorption on magnesium mitigate surface reactions, so they stabilize the magnesium, and then as we start to be dynamic, then we change the impedance as I showed. So the high impedance is not a real problem once the system starts to work. So I'm afraid that even with this excellent solution, in order to really demonstrate sagging efficiencies which are close to what we need, it should be nearly 100% if we want to talk about thousands of cycles. Then we may need chloride containing solution, but then we have to struggle with cathode that can manage with them. Now we see in this consortium, we see several interesting solutions. First of all, sulfides. With sulfide, the issue of the chloride. Chloride can manage with sulfide. Even they have catalytic effect, and they are good for sulfide. And also with redox polymers. So if we use redox polymers or sulfide, even we can use sulfide-coated oxide. At Bar-Ilan University, there is work on sulfide-coated vanadium oxide, which show promising results. So and the chloride issue, the problem with chloride and high voltage transition metal oxide cathode, high voltage high capacity oxide, is only surface. It's a surface issue, and this can be alleviated if we have some coating by sulfide. And that's it. I believe that I am done with my talk. And thank you very much.